In this video series, I'm going to derive and use the Green's functions for the Laplacian and for the gradient. The Laplacian is just a del squared operator, and we want to find a function so that the del squared of g of x prime is the three-dimensional delta function of the difference of x minus x prime. Similarly, we want to find, given a differential operator that is just the gradient, we want to find a function, a different function, g of xx prime, for which grad of g of xx prime is the three-dimensional delta function. This is because the delta function is a scalar operator and the gradient is a vector operator. This necessarily implies that we're going to want to find a vector valued operator for which the grad wedged with g is 0 and grad dotted with g is the delta function. So we're going to do that, and we're going to apply it to a couple gradient equations to get their solutions. But we're still going to start off with the Green's function for the Laplacian. We're actually going to use that to derive the Green's function for the gradient, which is pretty cool. So in order to solve our Laplacian, we have our Laplacian equation, del squared f of x equals g of x. We're going to use Fourier transforms. So we'll Fourier transform the whole equation. We'll write our Fourier transforms in the symmetric form, where we have 1 over 2 pi to the 3/2 as the leading coefficient, and e to the ikx, f of x d3x, e to the minus ikx f hat of k d3k, with our spatial volume element and our momentum space volume elements. There's our translation from position space into momentum space, and a translation back from momentum space back to position space. And here is the Fourier transform equation that we want to evaluate. If we do this, we're going to find that we end up in trouble at the origin of our k-space volume. So we are going to shift our origin by introducing a fudge factor of mu squared. So we add this fudge factor of mu squared here. We'll see how this gets us out of trouble, and we'll be able to evaluate and invert our Fourier transform relationship. Let's do that. So first thing we have to do is we have to figure out what is the Fourier transform of grad del squared f. We can start with an easier problem and say, what is the Fourier transform of just grad f? So that is 1 over 2 pi to the 3/2 of e to the I k dot x grad f d3x. And grad f is the sum over all m of e to the m ddx m f. So that's our grad f. What we're going to want to do is we want to take this whole integrand, we want to rewrite it as a full derivative with respect to d dxm, and then subtract off the other portion because we don't actually want the full derivative. So what we're left with is e to the m times d dxm of e to the I k dot x of x minus e to the m d dxm e to the I k dot x all times f of x. There's our integrand rewritten. There's a chain rule in reverse. And this is going to be about this term. We'll evaluate that integral over, so we'll have a integration of d dxm e to the I k dot x f of x dxm for all xm. And that will leave us with a double integral where we'll evaluate one of those integrands to start with, and that one will be e to the I k dot x f of x evaluated between xm equals minus infinity and positive infinity, and we presume that that f of x goes to 0 at the boundaries, all the boundaries of all the coordinates. So at the edge of the infinite sphere, f of x vanishes. So if that's the case, this whole term is killed, and we are left with just this contribution. So let's write that out. So we have here that del squared, or we are just doing del to start with. So grad Fourier transform of grad f is 1 over 2 pi 3/2 minus e to the m, and if we take our derivative d dxm of ikx, we will bring down the ikm term times minus, or not minus, plus. The minus was already accounted for. We had a minus here. I pulled it out. So we now have plus ikm e to the I k dot x f of x d3x. Which is minus ik f hat k. Nice. All right, so there's a Fourier transform of grad f. So if we take the Fourier transform of grad squared f, we'll bring down to minus ik squared f hat of k. So now we could say that grad squared minus mu squared f equals g in momentum space is minus I squared is plus I squared, which is minus 1, so minus k squared minus k squared plus mu squared f hat of k equals g hat of k. Good. There is our momentum space equation that we want to invert. I'll rewrite this slightly to put it in the form that we want to invert. We have f hat of k equals minus g hat of k over k squared plus mu squared. You could say that this is full solution of a problem. For any g of x, we can find g hat of k, and that gives us f hat of k. Just divide by k squared plus mu squared, then inverse Fourier transform, and we're done. We want to try to pre-evaluate this relationship so that we can do it in position space without first having to go as an intermediate into momentum space. So let's try that. So in position space, we have f of x is minus 1 over 2 pi 3/2 of g hat k e to the minus I k dot x d3 not x but k over k squared plus mu squared. Getting closer, which is minus 1 over 2 pi to 3/2. And I'm going to put in the form of g hat of k. So g hat of k is just the integral of f of g of x e to the I k let's say x prime, k dot x prime, d3x prime, k squared plus mu squared, e to the minus I k dot x, d3k. Okay, we're getting there. Actually, we've gotten far enough that we can actually write out the full solution of f. So we can say f of x equals the convolution of x, g of x prime with g of x prime d3x prime, where g of x prime is minus 1 over 2 pi. And I made a mistake up here. When I write out the g hat of k, I should bring down another 2 pi to the 3 halves. I didn't do that. That kills the square root. So we're left 2 pi cubed times, so I've taken the g hat dx prime here, and what is left is e to the minus I k dot x minus x prime d3k over k squared plus u squared. There we go. That is the full solution. But we want to go farther. We want to take this and evaluate it. It's not a particularly well-behaved integral with the infinite oscillation in the numerator, and it's so poorly behaved that when we take it to Laplacian later, we get a delta function. But let us go and figure out exactly what way this is poorly behaved. So to do this, we're going to switch to spherical coordinates. So let's say we have E1, E2, E3. We have vector in K space. That comes at an angle phi in the xy plane or the K1, K2 plane, theta here, so that our z-axis component of K has magnitude K cos theta, and our K1, K2 plane component of K has magnitude K sine theta, and our total value of K is going to be E1, e to the E1, 2 phi sine theta plus E2 cos theta. There we go. I've taken the liberty of using the geometric algebra expression for the xy plane component using a exponential notation for the rotation. And with that, you can write this out in coordinates if you like, one for E1, one for E2. We don't actually care because we are going to declare that we fix our axes in such a way that x minus x1 is E3 times the magnitude of x minus x1. So now we are looking at our k dot x minus x prime term, which is nothing more than, and this is k magnitude times that. So k dotted with x minus x prime, these are all vectors, is going to be the, it's not E2, but E3. So we have a magnitude of k times cos theta times x minus x prime. That is our k dotted with x minus x prime component in our integrand. And we were going to go plug in our k-space volume element and see what we can do with this guy. So I'm just going to minus 1 over 2 pi cubed. Let's plug that in. So G is minus 1, 2 pi cubed e to the minus I k cos theta x minus x prime k squared sine theta d phi d k all over k squared plus mu squared. And we have a triple integral with k going from 0 to infinity, with phi going from 0 to 2 pi, and theta going from 0 to pi. All right. We could start off by evaluating our d phi integration, which is just 2 pi, which will kill one of our 2 pi's downstairs. And let's write that out. We'll also make a change of variables. We'll say that u equals cos theta. So du equals minus sine theta d theta. So sine theta d theta is minus du. And we have cos theta going from 1 to minus 1. All right, so g is minus 1 over 2 pi now squared times k equals 0 to infinity dk k squared over k squared plus mu squared and u goes from 1 to minus 1 to the minus I k u, and I think that let's write alpha as x minus x prime. Alpha over nothing, don't need a denominator yet, k du minus, which makes this plus. All right. We can go and evaluate this integral. This is a trivial integral, just an exponential integral, and we get 2 pi squared, 0 to infinity, dk k squared plus u squared e to the minus I k u alpha over minus I k alpha in between 1 and minus 1. We have a k squared here and a k here. So one of those k's cancels out. And minus I alpha is a constant. We can take that out of the integral. We're going to be left with an odd function of k divided by an even function of k and an exponential. And that will be important because we're going to see how we can change this integration range from 0 to infinity, from minus infinity to infinity. So if we do this, we get minus 1 over 2 pi I over 2 pi 1 over alpha dk k over k squared plus mu squared times e to the plus ik alpha minus e to the minus ik alpha. And k is going from 0 to infinity. Let's look at this part of our integral, and we're going to make a change of variables there. So here we're going to say k goes to minus k. So k dk goes to minus k times minus dk, and k squared goes to k squared. We are left with minus 1 over 2 pi I 1 over 2 pi alpha times the integral from 0 to infinity of, I'm just going to say, integral from 0 to infinity plus the integral from 0 to minus infinity, but it is minus of k dk k squared plus mu squared e to the I k alpha. There we go. Now this guy is plus integral from minus infinity to 0. So we add these up. We now have the integral from minus infinity to infinity. All kind of works out nicely. And we're left with g of x prime equals minus 1 over 2 pi I 1 over 2 pi alpha integral from minus infinity to infinity of k e to the I k alpha over k squared plus mu squared. All right. This 2 pi I factored it out this way because it's just screaming at us to use contour integration. It says this is a residue result. So let's use the hint that we're given, and we want to evaluate our integral where we have poles at plus and minus I mu. So here's plus I mu. We have one pole and we have another pole at minus I mu. So this suggests that we want to attempt an integration contour that is either an infinite semicircle in the upper half plane or an infinite semicircle in the lower half plane. We have to figure out which contour is appropriate for this particular integral. So if we look at our numerator, that's going to be the key. So we have e to the I k alpha. And let's say that we make a parameterization of k. K is now a complex number. K equals k e to the I theta, where k is going off to infinity. This is our big K now instead of a little k, or a script k, or a vector k. So at that point, we have, on the semicircular contour, we have I big K times cos theta plus I sine theta times alpha, which is e to the I k cos theta alpha times e to the I squared, which is minus big K sine theta alpha. Now, k is positive, going to positive infinity. Alpha is positive, that's x minus x prime in absolute. And sine theta is, we need a negative for sine, a positive for sine theta, so that whole term is negative. And sine theta in the upper half plane is strictly positive. So that means we want to use upper half plane contour. So if we use the upper half plane contour, let's rewrite this one more time. I'm just taking a look at it. So g of xx prime is minus 1 over 2 pi I, 1 over 2 pi alpha, k e to the I k alpha dk over k plus I mu times k minus I mu, and we want to evaluate this around the pole. So Jordan's lemma tells us that the contribution on this big circular arc, infinite circular arc, is going to be 0. So if we evaluate the integral along this contour, which we can deform to an integral just around our pole in a positive sense. Then the pole at k equals I mu. So this is our pole term, and our residue is going to be the rest. So our residue is going to be evaluating this portion of the integrand at k equals I mu. So we get minus 1 over 2 pi I times 2 pi I times 1 over 2 pi alpha times k e to the I k alpha over k plus I mu evaluated at k equals I mu. There is our integral. That's our g. Our 2 pi i's are killed. We are left with minus 1 over 2 pi alpha I mu over 2I mu e to the I mu alpha. I mu's are killed. 2 pi alpha becomes 4 pi alpha, and e to the I squared mu alpha is e to the minus mu alpha. All right, so we're left with g of x prime equals minus 1 over 4 pi e to the minus mu x minus x prime divided by x minus x prime. Whew. There's our Green's function. We've managed to successfully evaluate the triple integral in k-space and come up with a spatial representation. This was the Green's function for del squared minus mu squared. So that means that del squared minus mu squared g of x prime must be the delta function. And in particular, if we let mu go to 0 now, which we can do now that we've actually evaluated the integral, we find that del squared of minus 1 over 4 pi 1 over x minus x prime should be the delta function. So what I think we will do is call it a day, and we'll come back. We'll apply this Green's function to a few representative equations,